Welcome back to Integral Calculus. In this video, I want to talk about doing calculus with logarithms. Let me get my head out of the way and I'm going to dive right in. In previous videos, we've already established that the derivative of the natural log of u is u prime over u, and that the integral of du over u is the natural log of the absolute value of u plus some constant of integration. We've also established that the log of some other base I'll call a of x is the natural log of x divided by the natural log of a. And from that, if I want to take the derivative of log base a of x, well, I would take that natural log of a out, and it would be 1 over natural log of a times the derivative of the natural log of x. I'm running out of screen space, so let's just go across here. In general, that's 1 over, well, it would be 1 over natural log of a times 1 over x, but we usually write it as 1 over x times natural log of a. I will rewrite that in yellow so that it becomes part of our list. And I hope it's apparent to you that we don't really need a separate rule for the integral giving us log base a, because it's just off by a different constant, and we could just multiply that constant in front. So we're only going to end up with natural logs when we do integrals. There is no reason to have a log base anything else unless you want to go back and use this rule to simplify something if you happen to be dividing by the natural log of a constant. All right. So let's dive in here and take the derivative with respect to x of, say, the log base 2 of, I don't know, x squared minus 9. Well, the rule says when we're taking the derivative of a logarithm, we're going to end up with a fraction. The argument ends up in the denominator, x squared minus 9. The derivative of that argument ends up in the numerator. In this case, that's just 2x. And then in the denominator, we have to also multiply the natural log of our base, in this case 2. When we're using a natural log, well, the natural log of e is 1, so we wouldn't bother writing that down. Switching gears, let's take a look at something involving an integral. How about 3x squared plus 5 over x cubed plus 5x dx? Well, in this case, I see we have a fraction. And whenever I have a fraction involved, whenever I have anything messy involved, I start to look at where the most complicated part of the expression is. And so a new one for you to learn is that the denominator of a fraction is more complicated than the numerator. So to evaluate this, I'm going to immediately try a substitution, let u equal that denominator, x cubed plus 5x. And by doing that, I'll get that du is going to be 3x squared plus 5 dx. That is incredibly convenient for us because this does in fact just turn into the integral of du over u, which is the natural log of the absolute value of u plus some constant of integration, and then plugging back in, this is the natural log of the absolute value of x cubed plus 5x plus our constant of integration. All right. Next up, I want to look at a seemingly simpler integral. The integral of dx over 2x. The first time I saw this integral, I immediately said, well, let's just take that 1/2 out front, and then I have the integral of dx over x and the integral of dx over x is the natural log of the absolute value of x, and of course I have to add a constant of integration. But then I was working with one of my peers as a student when I first saw this integral, and they said, well, wait a second, we have a fraction, so I'm immediately going to let u equal the denominator of that fraction, 2x. Then du would be 2 times dx. And if I introduce an extra 1/2 in front, I can write this as 2 du over, I'm sorry, I'm getting ahead of myself, 2 dx over 2x, and then I can substitute in and call this du over u. And so I get 1/2 times the natural log of the absolute value of 2x plus c. So should it be the natural log of x? Or should it be the natural log of 2x? Interesting. Well, keep in mind that the natural log of 2x is the natural log of 2 plus the natural log of x. And so the natural log of 2x plus c is the natural log of 2 plus the natural log of x plus c. And natural log of 2 is just a constant. So I can modify my constant of integration to absorb the natural log of 2. That's the trick to understanding what happened here. The constant of integration in the yellow version and the constant of integration in the blue version are not the same constant of integration. I have seen battles between students, and when I say I have seen, I mean I was one of the two students battling over which one of these two things was the way to solve the problem. Don't be like student me. Learn from my mistakes. Remember that you can use properties of logarithms to rewrite things. And remember that if you have a constant, well, you can just absorb your constant into the plus c and make your life a lot easier. This sort of thing will probably come up if you're working with a partner, even if you're just checking an answer in the back of a book. All right, let's move onward. Now that we are something resembling comfortable with integrals that end up with logarithms, we can get to the fun stuff. In trigonometry, you learned that the integral of sine is the negative of cosine. The integral of cosine is sine. And then you had some weird ones. The integral of secant squared is tangent. And the integral of secant times tangent is secant. But what if you just had the integral of tangent? Well, tangent, remember, is sine divided by cosine. And now I can try a u substitution. Whoops, why did I show up? Oh, my controls are doing weird things today. Anyway, if I let u equal cosine of x, then du is going to be the negative of sine x dx. That kind of ran off of the screen to where my touchscreen isn't really behaving anymore. But that is supposed to say negative sine x dx. All right, so I've got the negative of the integral of du over u after doing my substitution, which means it's the negative of the natural log of the absolute value of u plus c. Substitute back in my value of u. This is the negative of the natural log of the absolute value of cosine of x plus c. And if you're looking at online resources, or you're looking at various textbooks, you will often see listed the integral of tangent x is equal to the negative of the natural log of the absolute value of cosine x plus c. But that's not what I learned. When I was a student, my professor said, well, let's take this negative and bring it inside. So this is the same thing as the natural log of the absolute value of cosine of x raised to the negative first power. Raised to the negative first power means take the reciprocal. So this is the natural log of 1 over cosine. And 1 over cosine is secant. So the integral of tangent is the natural log of the absolute value of secant. To me, this one makes a little bit more sense. It makes a little bit more sense to me that the integral of tangent is going to involve secant, because the derivative of tangent involves secant. The derivative of tangent doesn't involve cosine. The integral of cosine doesn't involve tangent. The derivative of cosine doesn't involve tangent. Sines and cosines work together. Tangents and secants work together. Cotangents and cosecants work together. So that's why I find it a lot easier to remember that the integral of tangent is the natural log of the absolute value of secant. Similarly, the algebra is a lot messier but follows a similar idea. The integral of secant of x, I forgot a dx up here. The integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x, plus some arbitrary constant of integration. Right. Definitely not as easy to remember as the other one, but you know, it exists, it works, and that counts for something. All right. So with the relationship between natural log and trig showing up in integration, I thought it might be interesting to look at what happens with the derivative. So I would like you to take a look at the natural log of the sine of x, which is definitely not what we got when we were taking the integral of tangent, but sines and cosines are closely related, so it should have something to do with that. All right, so take a few minutes, work through this derivative, see what you end up with, and I'll see you in the next video.